This is section 2.9 in Math 1114. This section is about matrix transposes. We're going to be finding the transpose of a matrix. It's a funny little exponent that looks like a T, and we'll do some things with it besides just finding it, of course. We'll see some properties. So let's first of all start with the definition of a transpose. The transpose of A, where A is a matrix, denoted A with an exponent of capital T, is found by interchanging the rows and columns of A. In other words, a row becomes a column and a column becomes a row. Next, let's look at an example. Suppose A is the matrix 1, 2, 3 in the first row, 4, 5, 6 in the second row. Find A transpose. Well, like we said, we're going to interchange the rows and the columns. So A transpose has a first row of 1, 4, a second row of 2, 5, and a third row of 3, 6. As you see, the first row of A becomes the first column of A transpose. The second row of A becomes the second column of A transpose. So not so bad so far, right? Note that if A is an M by N matrix, then A transpose would be an N by M. That's because we're transferring rows into columns, columns into rows. So the number of rows in A would be the number of columns in A transpose. And similarly with N columns in A, that would be N rows in A transpose. In the previous example, the matrix A was a 2 by 3 matrix, whereas A transpose was a 3 by 2 matrix. Now obviously if A is a matrix that is square, it's N by N, if I do the transpose, I'm still going to get an N by N matrix. But if I do have a different number of rows and columns, those two numbers are going to switch places. Okay, now the properties. And this is in the form of a theorem. If A and B are M by N matrices, and C is an N by M matrix, then we're going to have several parts to this theorem. The first part says that A plus B, quantity transposed, is the same thing as A transposed plus B transposed. Okay, now what this is saying is that if I need to add two matrices, A and B, together, I can add them first and then transpose them, like it says to do, or I could transpose them first and then add them. Now, if you remember too, addition is commutative, so A transpose plus B transpose is exactly the same as B transpose plus A transpose. So even the order in which the two matrices are located can be changed. I can have A transpose plus B transpose or B transpose plus A transpose. Okay, second part of the theorem. The quantity A times C transposed is equal to C transposed times A transposed. Now that might seem a little bit crazy as to why they change places. Now I'm not going to go into a long explanation as to why that happens, but I will point out this fact. A times C would be an M by M matrix. C transpose would be an M by N matrix. A transpose would be an N by M matrix. That's because A, if you remember, was M by N. So C transpose times A transpose would be an M by M matrix, which is the right size for what we wanted. Okay, now if we had tried to do A transpose first and then C transpose, we would have gotten an N by N matrix, and that obviously cannot be the same thing as an M by M matrix, especially if M and N are different. So it's very important that you realize that if you transpose a quantity, the order switches. Okay, so it would be C transpose first, then A transpose. Okay, third part of the theorem. If I have A transpose, transpose, Well, what that's telling me to do is to switch the rows and columns of A and then switch the rows and columns again. Well, obviously, if you switch them one time and then switch them again, you're going to switch them back. So A transpose transpose is A. Next part. If A is a square matrix, then the determinant of A is equal to the determinant of A transpose. Now this should make sense because if you remember how to do a determinant, we can use any row or any column. Well, if we want to do the determinant of A transpose, it's just that the rows have become columns and the columns have become rows, so we're going to have the same numbers that we're working with. Okay, last part of this theorem says if A is a square matrix and it's invertible, in other words, A inverse exists, then A inverse transposed equals A transpose inverse. So those two exponents can kind of switch places there. That's actually a much bigger deal than it might initially seem, and I'll show that to you with an example. Okay, find A transpose inverse if A inverse is equal to, in the first row, -1, 0, 2. In the second row, 4, -1, 1. And in the third row, 3, -2, 2. All right, what it's asked me to do is to find A transpose inverse, and it gave me A inverse. Now what I've seen people do, and it's not wrong, it's just longer, is I've seen people take A inverse, then go through the reduction to find A, then transpose A, then go through the reduction to find A transpose inverse. Okay, that's obviously a lot of work. And from that last part of the theorem, we learned that since A transpose inverse is A inverse transpose, all we have to do then is just transpose A inverse. How hard is it to transpose A inverse? Well, you just take A inverse, and the rows of A inverse are going to become the columns of A inverse transpose. Okay, so you can see there, the -1, 0, 2 was the first row of A inverse. Now it's the first column of A inverse transpose, and so on. So really that question was quite easy once we remembered the theorem. Okay, next a definition. If A is equal to A transpose, then A is called a symmetric matrix. So if I take the transpose, if I switch the rows and columns and nothing happens, I have a symmetric matrix. Let's look at an example. Say that I have A is equal to the matrix containing 1, 2, 3 in the first row, 2, 4, 5 in the second row, and 3, 5, 6 in the third row. Well, as you can see, the first row, 1, 2, 3, is exactly the same as the first column, 1, 2, 3. The second row, 2, 4, 5, is exactly the same as the second column, 2, 4, 5. And the third row, 3, 5, 6, is exactly the same as the third column, 3, 5, 6. So if I were to transpose A, nothing would happen. So A is equal to A transpose. And so A in this case would be a symmetric matrix. It's not symmetric to anything. That's, a lot of people get confused with the terminology. They want to say it's symmetric to, no. The way it works is A is just symmetric, period, end of sentence. Okay, another example. This time I've given you a 4 by 4. Again, you can see the first row, 1, 2, 3, 4, is exactly the same as the first column, 1, 2, 3, 4, and so on. So if I were to transpose this, I wouldn't change it at all. You can also tell another way. If you look down the main diagonal always goes from upper left to lower right. And then we compare entries across the diagonal. The 2 corresponds to the 2. The 3 corresponds to the 3. The 6 to the 6 and the 4 to the 4. The 8 to the 8 and the 9 to the 9. As you see, across the main diagonal, all of the entries correspond. Another way to think of it is the 1, 2 entry equals the 2, 1 entry. The 2, 3 entry equals the 3, 2 entry. So in other words, anytime I switch the row with the column, nothing is happening. I'm not making any actual changes. So here's another way to tell that a matrix is symmetric. Besides actually taking the transpose or comparing the rows and columns, you can look across the main diagonal and match up the entries. All right, that was the end of section 2.9. 2.9 was about transposes. As you saw, finding a transpose is pretty simple, and the only real tricky part of this is just to remember that you can switch the exponents around, and that'll save you a lot of work in the long run. So do some homework, of course, practice a little, and this section should go really well.